Hey there guys, welcome to the video. My name is Pushpinder Gill, and in this video we're gonna be talking about determinants. So let's go ahead and get started with that. Just give me a sec. Alright, so we're gonna be talking about determinants. So I'm gonna start with the system of equations. Let's suppose we have these equations that a1 into x plus b1 into y, that is actually equal to c1, and I have another system of equation, another equation that is a2 into x plus b2 into y is actually equal to c2. Now what I can do is, if I want to represent this information in terms of a matrix, or a combination of matrices, so then actually I can represent this as like this. This a1 is here, this a2 is here, this b1 is here, and this b2 is here. This multiplied by x and y, we get c1 and c2. Now if you're wondering how did I get this, just go ahead and watch the video in which we talk about the multiplication of matrices, in which we use the examples of a person having 3 pens and 4 pencils and 5 pens and 5 pencils, and we kind of did the multiplication and we got the answer. Even if you multiply this matrix with this matrix, this is what you're gonna get, and this is the result that you're gonna get. Now what is an analysis that we can actually make out from here? What is the analysis? Now if I kind of explore this system of equations, if I kind of explore these system of equations, I can write this equation as y is equal to negative a1 over b1x plus c1 over b1, and I can write the next equation as y is equal to negative a2 over b2x plus c2 over b2. Now if I talk about, now these are nothing but this is something which represent two lines. These system of equations actually represent two lines, and in how many different ways can the two lines intersect? So I'm going to show you those ways. The first way the two lines can actually intersect would actually be a very natural way, wherein they intersect at one particular point. That means over here I have a unique solution for x and y. That means I have a unique value of x and I have a unique value of y where these two lines intersect. Another way of me talking about the intersection is that when the lines are actually parallel to each other. So when the lines are parallel to each other, their slopes are same. So when the lines are parallel to each other, their slopes are same, which means in this case there's going to be no solution at all. That means that these two lines are never going to intersect each other. That means there's not going to be any solution. So in this case, the slope of both the lines is equal. However, the intercept of both the lines is not equal. So slope of both the lines is equal, but intercept of both the lines are not equal. Another way, that is the third way in which two lines can intersect, if these two lines are essentially the same lines. Now how can I define same lines? I can say x plus y is equal to 2, or I can say 2x plus 2y is equal to 4. Now both the equations represent the same line. So in this case I'm going to have infinite number of solutions, and there's going to be infinite number of solutions, and our slopes are going to be same, even our intercepts are going to be same. So these are the three different ways in which the lines can intersect, and how I'm going to relate to that. Now these are not only these are nothing just lines, and these are two lines. In how many ways can they intersect? They can actually intersect in this way. If they intersect in this way, that means if their slopes are not equal, then I'm going to get a unique solution. And what is the slope of this line? Now y is equal to mx plus c. M is something which represents the slope of the line, which means this is something which represents the slope of this line, and this is something which represents the slope of this line. Which means if negative a1 over b1 is not equal to negative a2 over b2, or let's call it, if a1 into b2, which is, if I just take this that side, is not equal to a2 into b1, then these equations will give us a unique solution, right? Then this equation will give us a unique solution. If this is not this, if there is an equality sign here, then we're gonna get these two cases. That means we are going to get and we're not going to get an unique solution. Well, coming more on that, now let's go ahead and try to get what is this here, a2 in a1 into b2. So this is that a1 into b2 is not supposed to be equal to a2 into b1, which means a1 into b2 minus a2 into b1, it's not supposed to be equal to 0, right? So that is the case. Now if I talk about this determinant, this matrix here, that is a1 a2 and b1 b2, now how will I get these values? If I multiply this into this, I'm gonna get a1 times b2, and if I multiply this into this, I'm gonna get a2 times b1, and that is something which is known as the determinant of this matrix, right? And we denote the determinant of this matrix by drawing two lines, which is kind of similar to the way we denote a modulus function, but in terms of matrix, this means the determinant of that matrix, right? So I suppose you're understanding this point over here. It is also denoted as like this, kind of a small triangle for that matrix here. So if I say there is a matrix, that matrix A is actually equal to A, B, C, D, then the determinant of that matrix will actually be equal to the determinant of A, B, C, D, which will actually be equal to A into D minus B into C. Right? So I suppose you're understanding this point over here. That is the importance of this determinant. And if this is equal to 0, then we're not going to have unique solution, which means if the value of determinant is equal to 0, then we're not going to have unique solution. If this is not equal to 0, then is the only way we can actually get unique solution to our system of equations. Right? So I suppose you're understanding this point over here. So now let's try to find how we are going to get the determinant of a matrix which is of order 3 by 3. So let's suppose we have a matrix here. Let's suppose we want to find this determinant, and we have these numbers here, that is a11, a12, a13, then we're gonna have a21, then we're gonna have a22, a23, then a31, a32, and a33. Now let's suppose if I want to find the determinant of this matrix over here, right? So actually there are so many ways of finding out this determinant. I'm going to show you the one way, and I'm going to connect all the different ways that you can actually find the determinant using this here. So what you're going to do is, initially you're going to fix a row or a column. So I'm going to write down the steps here. Okay, so step 1 is to fix up a row or a column. So you fix up a row or a column. Let's suppose I'm going to fix up this row right here, right? So this is what I'm going to do. I'm going to fix up this row. Now once you fix up a row or a column, then what you do is you start with its first element. So what you do is you start with its first element. So I'm going to start with this element right here, that is a of 1 1. So what you do is, so I'm just going to keep it like this, you're going to write a of 1 1 into minus 1 raised to the power 1 plus 1. So what you're going to do is you're going to write that first element here, a of mn, and then you're going to multiply negative 1 into m plus n. So that is what you're going to do, and then you're going to multiply it with the determinant of, so what you're going to do is we have actually fixed this element here. So what I'm going to do is I'm going to forget these terms, and I have just these elements left here, which means I'm going to find out the determinant of these elements which were left. That is these elements. Then what you're going to do is you're going to start with the second element. So then what we're going to do is we're going to find out the determinant. Then what we're going to do is we're going to go to the second element and perform the same steps again. So what I'm going to do is I'm going to add, and I'm going to go to the second element, that is a12, and then I'm going to say negative 1 raised to the power 1 plus 2 into the determinant of, so what we're going to do is we're going to forget this column, we're going to forget this row. That means we're going to have this, and this left. That means we will be having a21, a23, a31, and a33. So then what we're going to do is, again we're going to go to the third element and again perform the same number of steps. So what we're going to do is now we're going to go to this element, that is a of 1 3. Now hum with me here, negative 1 raised to the power 1 plus 3 into the determinant of. So we're going to forget this line completely, because we're talking about this element, and we have only these four elements left, which is A21, A22, A31 and A32. And I suppose you know how do you find the elements. So this is going to be negative 1 raised to the power 1 plus 1, which is negative 1 square, which is actually equal to 1. So A11 into, so how are you going to find this determinant? This into this minus this into this. So it's going to be A22 into A33 minus A32 into A23. Then this one is going to turn out to be a negative 1. So I'm going to have negative A12 into this into this minus this into this. I suppose you got the idea now. And again, this is going to turn out to be positive 1. I'm going to have A13 into this into this minus this into this. So A32 minus A31 into A22. Right? So I suppose you're understanding this point over here. Now, one more important thing that I know I should have said before, that determinant can only be calculated for a square matrix. So it can only be calculated for a square matrix. It cannot be calculated for a rectangular matrix there. Right? So suppose you're understanding this point over here, guys. Now there are few points that I would like to say that again, few points. We have actually fixed up this row. We could have fixed up this row and done the same thing. We could have fixed up this row, done the same thing. We could have started with these columns and done the same thing. We could have started with these columns and done the same thing. This column and done the same thing. So pretty much you can fix up any row and any column just the way we did here. So what we're going to do is we're going to fix up the row or a column which has a lot of zeros, so that at the end of the day, our calculation is much easier, and no matter which row you fix or which column you fix, your answer is going to come out to be the same, right? So that is something that you can verify for yourself, kind of a homework for you, right? So that's there. And another small thing is that we always multiplied with negative 1 raised to the power something. We always do that minus 1 raised to the power I plus j. That totally depends on which row and which column you're fixing up. And this is something that you do. And if I plus j is actually even, then it turns out to be 1. If I plus j is odd, then it turns out to be negative 1. Something that you must really know, because negative 1 square is 1, negative 1 cube is negative 1, negative 1 raised to the power 4 is 1. Right? So that is there. And one more observation that I would actually like you to know, like you to observe, is, let's suppose if I'm going to start with an example here. Let's suppose A is a matrix. Let's suppose A is this matrix and B it's this matrix, right? So let's suppose these are the matrix we have. We clearly know from here that A is actually equal to 2 times B. We clearly know that A is equal to 2 times B, because if you multiply B into 2, you're going to get A. Now, what can you observe about its determinants? Well, determinant A is 2 minus 8, which is actually negative 4. What is determinant B? That is 1 minus 2, which is actually equal to negative 1. So we have determinant A to be equal to negative 4, and we have the value of determinant B to be equal to negative 2. So what happened to their determinants? Now we know that determinant A is actually equal to 2 to the 1 times determinant B. Something that we can clearly observe, that negative 4 is equal to 2 times negative 2. Something that we can clearly observe here. Now from here, I actually want to generalize one thing, that if matrix A is actually equal to K times matrix B, if matrix A is actually equal to K times matrix B, then the determinant of, and they both are of order n. The order of this matrix is n. So you can clearly see the order of this matrix is n. Okay, I've made a simple mistake here. This is 2 into 0, so it's gonna be 0 here. So 0 minus 8 is negative 8, and this is negative 8. This is 2 raised to the power 2 into B. Right? Sorry about that. Now this is what we have. So if A is equal to K times B, then the determinant of A will actually be equal to K raised to the power n into the determinant of B. So that is what we have. Want to verify that? Let's go ahead and verify that. Let's say that we have matrix A, which is actually equal to 1 1 1 1. Let's suppose this is a matrix, and we have another matrix B, which is actually equal to, let's not say 1 1 1 1, let's say 16 16 16 and 16, and we have another matrix which is 2 2 2 2. Now we clearly know that matrix A is actually equal to 8 times matrix B, which means the determinant of A should actually be equal to 8 raised to the power 2 of matrix B. Why is that? Because if A is K times B, then the matrix of A is K to the power N into matrix of B. Something that we generalized in the previous scenario there. Now if we trying to find the matrix of A, which is actually going to be equal to, now we're gonna get a 0 here, so let's change our example a bit. Let's say that this is actually equal to, we have 8 times, right? So let's suppose this is 0 and this is also 0, right? So similarly, still A is actually equal to 8 times B. Now 16 into 16 is 256, minus 16 into 0 is 0, so I'm gonna get 256. And matrix determinant of B is actually equal to 2 into 2, which is 4, 4 minus 2, which is actually equal to 2 here. Again, I'm making the same mistake. It's 2 minus 0, 4 minus 0, which is actually equal to 4, because 2 into 0 is 0. So I can say that the matrix of A, which is equal to 256, is actually equal to 64 times, which is 8 square, matrix of, sorry, the determinant of B. So 256 is actually equal to 64 times 4, which is equal. So this is an important generalization, that if A is actually equal to K times B, then the matrix, then the determinant, then they are of order n. Order means 1 2 3 and all the way. That means the determinant is going to be K to the power n times the determinant of B, right? So let's go ahead and end this video with an example of us trying to find the determinant of this. So let's suppose we want to find this value of determinant, that is 1 2 4, negative 1 3 and 0, 4 1 and 0. So let's suppose we want to find the determinant of this. So what we can do is we can actually fix up any row or any column. And which column are you going to fix up? I'm going to fix up this column. Why? Because it has a lot of zeros. So I'm going to fix up this 4. So 4 into negative 1. Now what is this 4? This is something which is known as A. It's the first row and the third column. So raised to the power 1 plus 3 into the determinant of, this is gonna go, this is gonna go. I'm gonna have negative 1 3 4 and 1 plus, I'm gonna fix up this 0. 0 into anything is actually 0. I'm gonna fix up this 0. 0 into anything is actually gonna be 0. So I'm gonna have 4 into negative 1 raised to the power 4, which is 1 into minus 1, which is minus 1, and 4 into 3, which is 12, right? That means this is gonna be 4 into negative 13, which is actually equal to negative 52. So even if you fix up this one or this one or this one, whichever you fix up, you're going to get this answer that is actually equal to the determinant of this matrix here. So I suppose you're understanding this point over here. I'm just going to do one more example with you. Let's suppose we're going to do this example 1 2 3 4 5 6 7 8 9, and I want to find the determinant of this matrix. Let me go ahead and fix up this row over here, because looks like an easy one once I fix up 1 2 and 3. So I fix up 1 into negative 1 raised to the power 1 plus 1, because this is A11, into the determinant of 5 8 6 9, plus I'm going to fix up this 2, so that is 2 into negative 1 raised to the power, this is something 1 plus 2, into the determinant of 4 7 6 9, plus 3 into negative 1 raised to the power 1 plus 3 into the determinant of 4 7 5 8. So whatever I get, I'm going to get as the answer, right? So I suppose you're understanding this point over here, guys. So thank you very much for watching this video, and make sure that you explore this website. You can ask me questions free of cost on this website. So make sure that you explore this website, and a lot of exciting stuff here. And give us your valuable like on facebook.com/perfectscores, and give your valuable feedback at perfectscores89@gmail.com. So this would be about this video, guys. In the future videos, we're going to be talking about the properties of determinants and a lot of different things that you can actually do with determinants. So this would be about this video. Thank you very much for watching. I'll see you in the next one.